we present Steering Your Generalist, Improving Robotics Foundation Models via Value Guidance. Large general-purpose robotic policies trained on diverse demonstrations have been shown to be effective to acquire high generalization capabilities. However, these datasets are generally of mixed quality, and recovering high-performing policies from such suboptimal data presents a major challenge. To motivate this, we begin by investigating failure modes of generalist robotic manipulation policies. We found that the policy encounters failures such as dropping the object too early, holding onto the object for too long, and the failure of precise grasping. While these failure cases may vary among different policies and scenarios, they highlight the room for improvement of generalist robotic policies. How can we improve the precision and robustness of generalist robotic policies while still retaining the best benefits of their pre-trained capabilities? In this paper, we propose Value-Guided Policy Steering, or VGPS, a novel approach to improve the performance of pre-trained generalist robotic policies. The key insight behind VGPS is to use a value function learned via offline reinforcement learning to re-rank the actions sampled from the pre-trained policy. Our recipe does not need to fine-tune the policy or even access the policy's weights and can be integrated with any off-the-shelf policy. In our experiment, we show that VGPS can address the failure modes and improve the performance of various generalist policies. Our recipe first trains a language-conditioned value function on a robotic dataset and then use the pre-trained value function to re-rank the actions from the generalist policies at test time. The main component of our method is a language-conditioned Q function that pre-trained on robotic demonstrations by offline RL. Given a camera observation and a language prompt, they will first be processed by a resonant encoder with film conditioning, and the actions are then concatenated with the output, and finally, a scalar Q value is predicted. Once we pre-train the value function, we can use it to steer any generalist policy upon deployment. Specifically, at any given time step, we first sample K action candidates from the generalist policy, and then we query the value function to get scores for each action candidate. Given these scores, we sample the action from a re-ranked categorical distribution obtained by these scores and execute the sampled action. This recipe can be combined with any pre-trained policy in a plug-and-play manner at test time. In our experiment, we evaluated VGPS across 12 tasks, 2 embodiments, and 5 generalist policies. Our first research question is, can VGPS address the failure modes and improve the generalist policy? To answer this question, we evaluated VGPS on a number of real-world manipulation tasks. We first begin by showing qualitative videos. In this mushroom task, the octo policy tends to drop the mushroom prematurely so that the mushroom does not land on the cloth. In contrast, combining our method can largely address this issue, leading to improved success rates. In this put sushi in pot task, we observe cases where octo policy does not release the object in a timely manner, hold on to the sushi for too long. However, VGPS's value function can rank and select the critical action and drop the sushi at the right time. Finally, octo also suffers from imprecise grasping since the surface of this plastic pepper object is slippery. Combining VGPS makes the robot grasp it more reliably, leading to improved performance. Quantitatively, we evaluated VGPS on top of octo policy on 6 tasks across 3 different real-world scenes and achieved consistent improvement over all tasks. Our second research question is, can VGPS improve various generalist policies across different embodiments? To answer this question, we conducted a further evaluation in the simpler simulated evaluation suite. In these evaluations, we used the same single VGPS value function and combined it with 5 different generalist policies, including Octo, OpenVILA A, and RT1X, and evaluated it across 6 tasks in 2 different embodiments. As shown in the table, VGPS improves the success rates of all 5 generalist policies across multiple embodiments using a single generalist value function trained on cross-embodiment data for all policies and tasks. In summary, we propose VGPS, a novel approach to improve the performance of pre-trained generalist robotic policies. VGPS re-ranks the action from generalist policies based on a value function learned via offline RL, which can address the failure modes and improve the precision and robustness of generalist policy, and our recipe can be integrated with any off-the-shelf policy.